In this video, I'd like to talk to you about Module 1. Module 1 is Single Area OSPF. OSPF is a link state routing protocol. It was developed as an alternative to the RIP routing protocol. The RIP routing protocol worked out great in early networking, but it does have its limitations. One of those limitations is the hop count metric that's used. So that's the only metric that's used for RIP. Your hop count is the number of routers that your data must pass through in order to reach a destination. And with that being the only metric that RIP was using, that meant that it did not take other things into consideration, such as bandwidth or delay or load or how reliable a network. It's just looking for the shortest path, period. Whereas OSPF does have an advantage over RIP in that it converges quicker and scales better because it's looking at more than the hop count in order to calculate the distance from one link to the next. So for example, OSPF, if it had two different routes to go and one had a higher hop count, but it was a much faster connection, it would choose to use that rather than using fewer hop counts to get to a destination on a slower link. Okay, RIP did not do that. RIP would look at the shortest path, and that would be it. So OSPF definitely became a better, more scalable routing protocol. So that's why it's more popular. Now, it's important to understand the components and understand everything with OSPF. Now, OSPF, I'm going to give you a little bit of info here. OSPF is a link state routing protocol. So that means it only sends changes when there's been updates to the network, instead of sending a whole bunch of routing updates. That's what RIP did. RIP would send a routing update every 30 seconds. Whether it needed to or not, whether there had been any changes. But OSPF does not do that. So it also uses hello messages to announce itself to each of its neighbors. And when two interfaces are trying to develop an OSPF adjacency, they decide on all the parameters, such as timers, a hello interval, and a dead interval. They also, excuse me, they also decide on other information as they're forming an adjacency and starting the communication process. Now, what they do is actually take the information from other routers and they build various databases. OSPF is a hierarchical routing protocol and it can be used in two different ways. So it can be used with one big area over an entire network, or you can divide that up into several different areas. When you divide into several different areas, as you'll see in a minute, there are several different advantages to having smaller areas. So we will look at that. And then they also, nominate or vote or whatever you want to call it. They pick designated and backup designated routers if you're working in a multi-access or broadcast type network. So those are some of the things that we'll look at in the chapter. So looking at your different components of OSPF, you see that they send several different types of packets. It's important to know your different types of packets. We will look at these. They exchange messages. You see hello packets, database description, link state requests, link state update, and link state acknowledgement packets. So we'll look at these in detail. OSPF messages are also maintained in various databases as well. There are three types of databases, and you see these listed here: the adjacency database, a link state database, and a forwarding database. Now, your adjacency database is what's used to build the neighbor table. This is a list that each router has of its own neighbors. Okay. That is not the same thing as an overall view of the topology. That is done in the topology table. And the topology table is built on the link state, using the link state database. The third table that's used is your routing table. So when you issue the show IP route command, you will see the routing table, and that's what the router uses to determine where to forward your data. The router uses the Dijkstra algorithm to calculate each path. So it uses the Dijkstra algorithm that is mentioned right here. This algorithm creates a whole tree by placing each router at the root of the tree and then calculating the shortest path to get to all the other devices. And then from there, that's how they choose the best route. And that's the information that's placed into that forwarding database, or in other words, your routing table. So what you're viewing in the routing table is just one of the 3 routing tables, but those other 2 tables used information to calculate what's in the routing table. Here's your different types of packets and the processes that OSPF uses. So the first thing that's done is they establish neighbor adjacencies. They do that through exchanging hello packets. So each router sends hello packets to the other routers. They do that through all the OSPF enabled interfaces. The reason I say that, I'm pointing out that, is because you can have more than one routing protocol on a router. So each one has to be enabled to use OSPF, or it does not share with the updates in the other packets that are being sent. So after it establishes an adjacency, they exchange what's called link state advertisements. These link state advertisements, or LSAs, contain the cost associated with a link. Now, there's cost associated with each type of link based on the speed of the link. So, for example, a 56K modem would not be the same cost as, say, a T1 line or another type of faster connection. So after the link state advertisements are received, those OSPF enabled routers build your topology table. So remember, your topology table gives the devices an overall view of the entire topology that's being used. And then that tree is created that I mentioned earlier. So this is the view that that router sees. So it's kind of at the top of that tree, and then it's showing the view that it has for each path to the other devices in the network. Once that's developed, then you start seeing that routing table being built. So you have a destination in your routing table, and then the path to each one of those. Now there might be 2 different paths to get to the same place. So that's where the OSPF protocol will actually determine which route is injected into the routing table so that you only see the best route that's available. You won't see everything that that routing protocol knows about. It's injecting its best route within that routing table. Now, I mentioned earlier that you can have single area and multi-area OSPF. So single area, you'll see that all the devices belong to the same area. When you configure it, you actually have to configure OSPF to a specific area. Now, if you divide it up into multi-area, that means you have more than one area. So area 0 indicates the backbone network, and then you have your other 2 areas. So why would you want to have multi-area? Well, there's several advantages to doing that. Each area is going to process its own information, which means less processing on the routers, because if there's an update to one, it doesn't go out to all of the devices in all areas. It stays within its own area. So if there's a little bit of instability located within the network, that'll kind of be hidden from the other routers as well. By having fewer devices, it also allows all the devices to converge a little quicker. And of course, that's going to be less bandwidth, and then you're going to have a little bit more control over your routing updates. So if you're looking specifically at the advantages listed in this curriculum, it points out your smaller routing tables, reduced link state overhead, reduced frequency of your calculations. Now, you can have OSPF version 2 or 3. OSPF version 2 is IPv4. OSPF version 3 is IPv6. Can you have both? Yes. OSPF version 2 communicates with other OSPF version 2 devices. OSPF version 3 devices communicate with other OSPF version 3. So, in other words, IPv4 communicates with other IPv4 devices. IPv6 communicates with other IPv6 devices. So you can have those both running, okay? Both running on the same devices. You do have a video here. I would recommend reviewing this video. Okay. This video will go over your different packet types, but this gives you a good summary of your packet types. You'll want to know these for your chapter exam. You'll want to know these for the CCNA exam as well, because I have seen this when I have tested on the CCNA exam. It's done in various methods. It could be drag and drop. It could be multiple choice. It could be any number of ways. But you'll want to know your packet types. So type 1 is your hello packets. This is used for adjacency or building your neighbors, discovering who your neighbors are. Your database description packet, or abbreviated as DVD. Okay. This is an abbreviated list of your devices. It's checking for the database synchronization between the different devices. So an abbreviated list of your link state database packets. Your LSR, or link state request, this is used for sending specific requests from one router to the next, requesting for specific information. The link state update is when it sends that specific information. And then the acknowledgement is acknowledging that it's received. So link state acknowledgement request. So make sure you review that information on your different packets. So I want to look at the packet content for OSPF. So you see you have all these different types of information that's located. I want to point out a couple of different things. If you're looking at a packet and examining that using Wireshark or some other method, you'll see a type field. The type field identifies what type of packet it is. Okay. So type 1 would indicate a hello packet, for example. Okay. You'll also see a router ID. Okay. We're going to talk a little bit more about router ID in just a minute, but that identifies what router it is. Okay. So it'll probably look like an IP address. You also have area ID to see. You can look at that and tell what area that came from. You can have your network mask, your hello interval. Okay. OSPF uses hello intervals. Okay. The default hello interval is at 10 seconds. Okay. It also uses a dead interval. Okay. The dead interval is the amount of time that router is going to wait to hear from a neighbor before it declares that it is down. Okay. So by default, the router's dead interval is 4 times that of the hello interval. So if your hello interval is at 10 seconds, by default the dead interval would be at 40 seconds. If you change that, it is possible to change a hello interval and a dead interval. If you change your hello interval, make sure you remember to change your dead interval. Now, your router priority. Your router priority is what's used for a designated router or backup designated router election. The default priority for all OSPF routers is a 1. Now you can change that. The higher the value, the more likely that router will become the designated router. If you don't want a router to become a designated router, you can change it to 0 and it would never be the designated router. And that's because the default is 1, or you could change it to higher. The designated router, which would be down here towards the bottom of the packet, that's the router ID of the designated router. The backup designated router would be listed here. That is the second highest router ID. The list of neighbors, okay, this list identifies the router IDs of the adjacent routers. Now, also make sure you review the 7 states of your OSPF operation. I could see this more than likely being a really good drag and drop exercise or multiple choice. Now, the operational states are the states that the router moves through when it's trying to reach convergence. So I've mentioned that term a couple of times, but in case you're not sure what I'm talking about with convergence, convergence is the term used to mean that all the devices have the same knowledge of the network. Okay, that's really important because you want all your devices to have the same knowledge of the network. The faster devices converge, the better, because they all have the same knowledge and you're not getting routing loops or switching loops or whatever. So the first thing that happens is they all start in a down state. They're not sending anything, no hello packets, or they're just starting to send hello packets from here. Okay. They haven't received anything, they're just kind of starting the whole process. And then you get this init state. That's when hello packets are actually received. So in the down state, they're starting to send them. They're actually received in the init state. So it kind of sets up a two-way state between two devices. You're kind of working towards that. So in your two-way state, that communication between both routers is going in both ways. If you're getting into a multi-access network, that's when routers are going to elect the designated router and backup designated routers. Now, if you're having a point-to-point network where there's only 2 routers, there's no need for a designated router and backup designated router because point-to-point, they're going to be able to communicate with each other. So if you're on point-to-point, the 2 routers will decide which one's going to initiate the database packets. In the exchange state, routers exchange the packets. And then if they need to send additional information, they can do that to transition to the full state. When they're at their loading state, the link state request and updates are used to get a little bit more information. Things start moving into that SPF algorithm that we looked at, and the state changes to the full state. The full state is where everything is synchronized and you get to that converged state that I was referring to earlier. Now, in order to establish neighbor adjacencies, those hello packets are going to be sent. When OSPF has been enabled on a router, the router tries to determine if there's another OSPF neighbor that's on the same link. So it does this by sending a hello packet that contains its router ID, and it sends that to all the OSPF enabled interfaces. The hello packet is sent out using the multicast address of the 224.0.0.5, and only the OSPF version 2 routers will process those packets. And the OSPF router ID is used by OSPF to identify each router within that area. The OSPF router ID is a 32-bit address. Now, if you're wondering how they determine the router ID is assigned as follows. You can either configure that using a router ID command. So it's just router ID and then whatever the valid address is that you want to use. If that's not used, then the highest IP address on a loopback interface is used. If you don't have a loopback interface, then it uses the highest IP address. Okay. So first of all, it's going to use the router ID. Then if we don't have one of those, then you'll use the highest loopback address and then the highest IP address on any of the active physical interfaces. So when a neighboring router or a neighboring OSPF enabled router receives a hello packet with a router ID that's not in its neighbor list, it tries to form an adjacency with that router. So again, it starts at the down state and then moves to the init state. Now, this is when it's sending out your hello packets. And that's what you're seeing in this diagram here. So in that case, I believe R1 sent one out to R2. R2 receives the hello packet from R1, adds the R1 router ID to its neighbor list, and then R2 sends a hello packet back to R1. When R1 receives that hello packet from R2, it also notices its own router ID in the list of neighbors within that hello packet. So when it receives that, it transitions into that two-way state because it realizes that R2 had received its information and it sees that in the packet that it also receives. So it knows it's gone in both ways. Once R1 and R2 are connected together, it goes through a process of selecting the designated router and the backup designated router. We'll look at that in just a minute. So you're looking here at the synchronization of OSPF databases. So after you get to that two-way state, the routers kind of transition into those synchronization states. Okay, so after the two-way state, the routers move to that synchronization state. Now the hello packets were used to establish neighbor adjacencies. The other 4 types of packets are used throughout that process between the synchronization. Now that's a 3-step process. So the first thing they do is decide who the first router is going to be. In that X-start state, the 2 routers decide which router is going to send the database packets first. So they determine that by using the highest router ID. So that's going to send the database description packets first during the exchange state. So in this scenario, R2 had the higher router ID, so it chooses to send it first. In the exchange state, the 2 routers are going to exchange their database description packets, and that's going to include information about the link state advertisements that are going to appear in the link state database of each of the routers. The entries can be about a link, they can be about a network. You can also have information about link state type, the address of the router. So here you see in this figure that it acknowledges the receipt of the database description packet using the LSA packet. So this is the scenario of R2 sending that packet to R1. R1 receives it, acknowledges the receipt. R1 sends the database description packets to R2, and R2 acknowledges R1. So there's a lot of acknowledgement that occurs within this routing protocol. R1 compares the information it received and compares that to its own database. If it has more current information in the update, that router then transitions over into the loading state and it updates the information that it's received. So after your link state updates have been sent, when everything is converged, then after that, those updates are only sent to neighbors if there's a change in the network, or it can be sent every 30 minutes. So why do you need a DR and BDR, or designated router and backup designated router? Well, if you're not careful and everybody's sharing all their information on a network where you have lots of routers, each router is sharing its information with another router, so they're updating their information that's received from one router, sending it back out to all the other routers. You can end up with a routing loop if you're not careful. You can end up with where everybody does not have the same common knowledge of the network, or no convergence. You also have an excessive number of packets or flooding of your link state advertisements. So there's lots of issues. So you can use this. If you'll look at 1.3.6, you can see an example of what the flooding would look like. But it's recommended that you would choose a designated router and a backup designated router, that they would be chosen within a network. Because if you do that, it'll manage the flooding of information, because the designated router will be the one that sends the information or disseminates all the information, as opposed to random devices doing that. So you can kind of see the role of the designated router here. Okay, so that device was sending the information out to everybody, but then you notice that the update only came from the designated router instead of all the other devices. So that would be the reason for choosing a designated router and a backup designated router. So how's a designated router chosen? That election process is chosen based on the router with the highest priority. So the router with the second highest priority becomes the backup designated router. The priority, again, is a number between 0 and 255. Again, the default is 1, as I mentioned earlier. If you set a router to 0, it won't be the designated router. And you can set it higher than 1 if you want. If you always want a particular router to be the DR, you can do that by setting the number. In the case of a tie where the default of 1 has been used for all the devices, the tiebreaker would then go to the router with the highest router ID. So then you would go back through that process that I mentioned earlier of the router ID, using the router ID command. If you don't have that, it would use the highest loopback. If you don't have that configured, then it would use the highest active IP address. So this is an overview of Module 1 and OSPF. In Module 2, we'll learn how to configure. You do have several exercises, and you have a great summary here on this next slide. So I'd recommend looking over all that. I would also recommend looking over all the videos in the chapter.